Okay, 10.2 is called independent and dependent events. All right, so let's start with independent events. The outcome of one event does not affect the outcome of another event. So this is when we've got multiple events happening. Okay, and here's the formula for it. Let's say we've got event A and event B, and we want the probability of these two independent events occurring. What we're going to do is take the probability of event A and multiply it by the probability of event B. Okay, so let's look at an example here. So here we have Stratos flipping a coin 5 times. All right, and flipping a coin is an independent event because each time you flip a coin is its own. It's going to be 1/2 probability of either tails or heads coming up. It doesn't matter what happened on previous tosses of a coin, assuming it's a fair coin. It's always going to be 50% chance of each thing coming up. Okay, so that's why it's independent. So here we're going to find the probability of the coin coming up tails 5 times in a row. Well, on the first toss, it's going to be 50%, 1/2 probability. The same thing will happen with each of these, right? So I'm going to multiply each of these probabilities together. So then, let's see. 1 out of 2 things that can happen is tails on each of these trials. And then I multiply it all together, multiplying straight. I need a common denominator, even though I have one here. You just multiply straight across. So on the top, I've got 1. On the bottom, I'm going to have 2 to the 5th, which comes out to 32. So I could say there's a 1 out of 32 probability of getting 5 tails in a row. Okay, if you wrote that as a percentage, it'd be 3.125%. Pretty small chance of 5 tails in a row, but it can definitely happen. Okay, all right, so here's another. Shira rolls 2 number cubes. Those are 6-sided dice, right? Find the probability that she rolls doubles twice in a row. So every time you roll dice, it's not dependent on your previous roll. That's not going to affect what you roll on the second roll, right? So this one's independent. So I'm going to find the probability of rolling doubles once, and then multiply that by the probability of rolling doubles again, like that. Okay. All right. So doubles. Let's think about it. You could do double 1s, double 2s, 3s, 4s, 5s, and 6s. So there's 6 different ways that you can get doubles when you're rolling 2 dice. And when that's the favorable outcomes. The total outcomes are going to come, well, on the first die, there's 6 things that can happen. On the second die, there's 6 things that can happen. This is the fundamental counting principle here. So there's 36 total things that can happen. Okay, and it's going to be the same probability on the second roll. So you could multiply these together right now, but you can also reduce them first just to make it a little easier. Otherwise, you'd have to reduce later. And then we're going to get 1 out of 30, whoops, I'm off screen, 1 out of 36 probability, which is about it's exactly 2.7 repeating percent. Okay. All right, next page, let's look at some dependent events. Okay, dependent events. So these are where the outcome of one event does affect the outcome of another. Okay, so the probability of 2 dependent events occurring is going to look like this. We're going to just take the probability of the first event first. Then this means it's the probability of event B occurring, assuming that event A has already occurred. The probability of event occurring assuming that event B has already occurred. Okay, and this will become clearer when I show you with an example here. But we're going to need this slightly different formula for dependent events, okay? So Cringer randomly is going to select 2 pieces of fruit from the bag without replacement. So Cringer's going to reach his hand in, pick out one of the pieces of fruit, but then he's not going to put it back in the bag, and then he'll choose a second event. So whatever he chooses on his first pick is going to affect the contents of the bag, and that means it's going to affect the probability of whatever else coming out on his second take. So that's why these are going to be dependent, okay, because we're not replacing the fruit. So 2 apples in a row, let's see, I'll write that like this, the probability of pulling an apple and then another apple. So let's see, that's going to be the probability first of just pulling an apple out, okay? And then we're going to multiply that by the probability of pulling an apple out, assuming that an apple has already been removed from the bag, okay? So the probability of pulling an apple out, well, there's 2 apples here out of 5 pieces of fruit. But then you got to imagine, okay, we've already pulled an apple out. Now on the second draw, there's only 1 apple left, and there would only be 4 total pieces of fruit left. So that second draw, you can see that it has been affected by what's been removed on the first draw. All right, and then you multiply straight across. So you'll get 2 over 20, which is 1/10 or 10%. Okay, all right, let's try another. So here Mumra randomly selects 2 pieces of fruit from the bag without replacement. So this phrase is the key that tells me that this is going to be dependent. If Mumra would choose a piece of fruit and then put it back in and then choose another, well, those would be independent. So if you replace it, it's independent. But if you don't replace the first piece of fruit you take out, that means we've got dependent. So now we're finding the probability of pulling an apple and then an orange. Okay, so we're going to take the probability of pulling out an apple first, which would be 2 out of the 5 pieces initially, right? But then we're going to multiply that by the probability of pulling out an orange, that's my second event, assuming that an apple has already been removed. Okay, so I'm thinking, okay, Mumra pulled out an apple first, so that one's gone out of the bag. Now I'm looking at the oranges. Well, there's 3 oranges left in the bag out of 4 pieces of fruit. So I've got 3/4 there. Then multiply straight across. I get 6 over 20. That'll reduce to 3/10 or 30%. Okay. All right, let's look at some more on the next page. We're going to look at a deck of cards. I used to assume that everyone knew the contents of a deck of cards, but I'm not so sure anymore. I don't think maybe people don't use them as much. So there's what a deck of cards looks like, a standard deck of 52 cards. We're going to look at the probability of pulling things without replacement. So that's the key phrase that tells me that these are dependent. So we're going to find the probability of pulling a king and then another king. So I'll just put K for king. Okay, and then on the second draw, we're going to imagine pulling a king, assuming that one of the kings has already been removed. Okay, so on the first draw, the kings, there's 4 of them out of 52 total cards. But if you, let's say you pick this king in that top right corner, well, on the second draw, there would only be 3 kings left out of 51 cards. So it's going to affect the amount of kings and the total amount of cards as well. So second draw, we'll get 3 out of 51. Okay, and you can multiply them right now. You could also reduce this first fraction. 4 over 52, you can divide 52 by 4, and it's going to be 13. So if you divide top and bottom by 4, we get 1/13. But you know, you could always just reduce at the end after you multiply too. So this will give me 3 over 663, and 3 goes into both of those, so you can reduce again. Okay, so pretty small chance of pulling 2 kings in a row, right? So if you're playing poker and that's what you need, not likely going to happen, but it could. It's about a 0.45% chance, less than 1% chance. Okay. All right, so let's try another here. Let's find the probability of pulling a king and then a queen, again, without replacement. I guess, I don't know why I wrote that again. But we're going to first find the probability of pulling a king, and then we'll find the probability of pulling a queen, assuming that a king has been removed. So pulling a king, same as before, that's 4 out of the 52 cards in the original deck. But then let's imagine we pulled a king out. Well, there'd still be 4 queens, but it's out of 51 cards. There's less cards in the deck now, right? Sorry, 4 queens out of 51 total cards left now, okay? And then again, I can reduce that first fraction just to make the numbers a little more manageable. Okay, and I've already done the multiplication here. That's what you get when you multiply straight across, and that actually doesn't reduce any further. So you could leave it like that, or that's about 0.6%. Okay. All right. Let's try another here. A blue and a red number cube are rolled. So these are dice, right? We got a blue die and a red die. It just has 6 sides. That's why we say the number cube. Okay, so find the probability that the blue comes up 2 and that the sum of the cubes is 7 or more. So these are 2 different things. These are 2 different events, even though we're just rolling the die once, okay? But these are going to be dependent because if the blue is 2, if the first cube is 2, it's going to affect the sum, right? The sum is what you get when you add the 2 numbers together. So let's think through this. This is going to be the probability of the blue coming up 2. And then we're going to multiply that by the probability of the sum being greater or equal to 7, assuming that we already know the blue cube is a 2. Okay? All right, so the first cube coming up a 2, well, that's 1 out of 6 things that can happen, right? So that probability is 1/6. All right, let's think for the sum. Well, the sum is we're gonna use both dice to get the sum. We're gonna add together the numbers from both cubes. So that means there are 36 total things that can happen because 6 things on the first die, 6 things on the second die, right? Anytime you roll 2 number cubes, there are 36 things that can happen. And let's make a little chart to find the, well, here, I'll do it over here, to find the favorable outcomes for the sum being greater or equal to 7, assuming the blue cube is a 2. Okay, so I know the blue cube has to be a 2, so I'm just thinking, how could I get 7 or more? Well, if I roll a 5, that's a 7. And if I roll a 2 and a 6 like this, that's going to be an 8. So both of those things are 7 or more. Those are the only favorable outcomes, right? Because we have to have the blue be 2. So there's 2 outcomes here that are favorable, and there's my setup, okay? And then I'm going to reduce the second fraction and then multiply, and we'll get 1 over 108, which is about 0.93%. Okay, next page. All right, here we've got an example. We've got, these are, this chart lists the members of an orchestra string section from the Durmstrang Institute. Okay, so we've got boys and girls playing these different instruments, and it just lists how many of each. Okay, so let's find the probability that a randomly selected student from the string section plays cello. Okay, so you can do this, you can kind of think about this as 2 different events, but when I have a chart like this, I just like to think, well, how many students are going to be in both of those categories, okay? So from the string section, that's everyone, right? So from the string section, there are going to be, the cello players are going to be these 2, right? So it's the boys and the girls that play cello, because it doesn't say anything about boys or girls here. It's just all the people that play cello. So the favorable is going to be 5. And then the total, I have to add everyone up. And if you add up all those numbers, it's going to be 16. Okay, so that one's pretty straightforward. But it gets a little bit more complicated on part B, because now it says find the probability that a randomly selected girl, okay, so we've got two different categories here, girl and from the string section, so that just means everyone up there, so that a randomly selected girl plays violin. So I'm still thinking favorable over total. It's just my total isn't going to be everybody. The total is just going to be the girls, because we're talking about randomly selected girls here. Okay? So then I'd add up all of the girls here. So for my total, that's going to give us 9. And I'm thinking, how many of those girls are going to play violin? Well, that's my favorable, right? So if you have a chart like this, you could do this with the formulas, but as long as you know favorable over total, you can kind of just pick out the pieces you need like that. And then this would be about, well, it'd be exactly 44.4 with the 4 repeating %. Okay? All right. And last up, let's find the probability that a randomly selected violin player from the string section is a girl. So this seems like it's the same because we got the same two categories, but it's a little different because we're randomly selecting a violin player. So this is going to be the total, and then the favorable is going to be the girl, the ones that are girls from the violin players. Okay, so this is a little different. So this time the total is going to be all of the violin players. We're randomly selecting a violin player. So violin players, there's going to be 6 of them. Okay, and then the favorable is just the girls out of the violin player, so it's going to be, again, those 4. So it's going to be 4 out of the 6, which is 2/3 or 66.6% with the 6 repeating. Okay, all right, that's the end of the section, and I'll see you next time.